fuzzer, I barely know her. Fuzzing is an automated software testing technique that involves providing invalid, unexpected, or random data as inputs to a computer program. The program is then monitored for exceptions such as crashes, failing built-in code assertions, or potential memory leaks. Sometimes hacking isn't about taking a program apart, it's about throwing random objects at it to see what breaks. There's two types of fuzzing, dumb and smart fuzzing. The dumb fuzzing, or mutation-based fuzzing, modifies existing values to create new ones. This obviously requires some kind of baseline input. We call this baseline input the corpus or seed of the fuzzer. This is like someone getting bitten by a mutated insect and developing superpowers, or someone from a super secret soldier program. Not that the US government would have anything like that. In generator-based fuzzing, the fuzzer creates test values from scratch. It does not use any kind of reference input, although it may use meta information. Sometimes it is also called generation-based fuzzing. Think of it like some hero or villain building a super powerful robot or cyborg from scratch. Bonus points if he does it in a cave. The concept of fuzzing was invented by Professor Barton Miller, who remotely connected to a Unix system during a thunderstorm. The interference noise on the dial-up link because of the thunderstorm caused applications that were using data off that line to crash. Because of this fuzzy input and fuzzy static, he nicknamed it fuzzing. Let me just show you what it would look like to use a standard fuzzer on some sample input. To this end, I've written us a little text file with a bunch of characters that all together spell out fuzz. We'll be using the fuzzer Zuff, and if we just run our sample input through it, we can see that a couple of the characters have just been changed into different characters. In fact, the whole character hasn't been changed, but just a few quote-unquote random bits in the text file that now make the numbers in it correspond to different characters. I say quote-unquote random because, as you can see, if you run it through again, it has the exact same output. This is because Zuff uses the same seed every time by default. What this also means is that if we run this twice, we will get our original input back. This is because, again, it's flipping the exact same bits both times. So all the bits it flipped the first time, it's just flipping back to their original orientation in the second fuzzing. So to actually fuzz this into a random looking input, we will just run this again, but with a seed this time. So we can take our original standard input again, run it into our little temporary file, and set our seed to be, let's say, 42. And you can see this time it has a different output than it did the first time. Different characters have been randomized, and they have been randomized to different characters than they were before. So this still looks pretty similar to our original input. So let's do that again. This time, let's use a different seed. In this case, let's do 87. And so this looks already a good bit more different. So let's do that one more time just to see how it looks. And let's use the seed 99. So you can see how piece by piece the fuzzer would change the input until slowly it becomes not even recognizable compared to the original input anymore. This way, without having to manually test it, programmers can just get a variety of inputs to all try against their program. However, there's no real logic to what it's doing to the input. It's just changing random bits until something sticks.
More specifically, we're going to take a look at the American Fuzzy Lop. No, unfortunately, not the rabbit breed. American Fuzzy Lop is a security-oriented fuzzer that employs a novel type of compile-time instrumentation and genetic algorithms to automatically discover clean, interesting test cases that trigger new internal states in the targeted binary. Well, what does that really mean? Basically, American Fuzzy Lop is a brute force fuzzer that has simple genetic algorithms built in, and it uses a modified form of edge coverage to pick up subtle local scale changes to program control flow. In fact, there are over 100 bugs that can be attributed to American Fuzzy Lop. The fuzzer takes an initial set of test cases to benchmark what is expected or considered normal behavior in the program, and then it creates the input queue. It begins by taking an item from the input queue, using targeted algorithms to mutate the input, and then uses these derived children as input to the target application. A monitor observes each execution, and where new behaviors are observed, the derived input which caused them is added back into the input queue so it can too be further mutated. Just because different behavior is observed from a test case from the input queue doesn't mean it's necessarily bad, it just means it's different. This can help the fuzzer even further create better coverage. And lastly, I'm going to be demoing AFL on my system. Here is our test program that we are going to fuzz. This is a very simple program that reads a pattern from the standard input, decodes it, and writes the result to the standard output. So for example, if you were going to input hello plus world %sign 21, it would output hello world exclamation point. So let's take a look at our test cases. As you can see, I've built out some test cases inside my AFL demo folder. And inside this test cases folder, I have 3 test cases that we're going to input into our fuzzer. So the first one is hello, the second one is hello plus world, and the third one is hello %21. And these test cases are going to be fed to the fuzzer, and the fuzzer is going to take these and mutate them to the point where they probably will be unrecognizable. But by giving these test cases to our fuzzer will sort of start to understand what our program takes and begin to learn things about our program. And all I have to do is run my fuzzer, so I'll do fuzz switch. And now it's all set and ready to roll. At this point, it's taking my test cases, and now it's going to fuzz the program. And this can take a really long time. Since this is a generative process, this could take hours, days to run through all possible mutations. And there are a few key things that American Fuzzy Lop tells us. So it's telling us over here how many cycles it's done, unique crashes and unique hangs, which is what we're interested in most, as well as the strategy they're trying. So bit flips, byte flips, arithmetics, known ints, all these things are telling us what the fuzzing strategy is yielding us. So flash forward 28 minutes and the fuzzer has found 567 unique crashes. So let's go investigate these crashes. So here are all the crashes that we've gotten from running the fuzzer, and as you can see, there are a lot. So what I'm going to do now is just send that crash into the standard input of my program and see what happens. And as you can see, we get a really weird little output here. And we can do that with any of the crashes that we found. And so this one has a completely different output, very different from Hello World where we started. And that is American Fuzzy Lop. Thank you for watching.